Let's begin with closed conduit flow, which means the fluid is fully enclosed within a boundary such as a water pipeline. When we say steady flow, we mean the velocity of the fluid at a given point does not change with time. When we say uniform flow, we mean that the velocity remains the same along the length of the pipe. In reality, most engineering systems deal with steady but non-uniform flow, where velocity may change along the pipe due to diameter changes, fittings, or pumps. In closed conduits, we classify flow into laminar flow, where fluid particles move in smooth, parallel layers with minimal mixing. Turbulent flow, where fluid particles move chaotically, with swirling eddies and mixing. The Reynolds number, Re, helps determine the type of flow. Re less than 2000, laminar. Re greater than 4000, turbulent. Between 2000 and 4000, transitional zone. 2. Flow of real fluids and friction losses. Unlike ideal fluids, real fluids experience energy losses due to viscosity and turbulence. The two main categories of head loss are major losses, due to friction along the length of the pipe, calculated using the Darcy-Weisbach equation. Minor losses, due to fittings, bends, valves, and sudden expansions or contractions. We often visualize the relationship between friction factor, Reynolds number, and relative roughness using the Moody diagram. The friction factor depends on flow regime, laminar or turbulent. Pipe roughness. Reynolds number. In turbulent flow, increasing surface roughness increases head loss, which is why smoother pipes are preferred for long-distance water transport. 3. Laminar flow and Hagen-Poiseuille's law. In laminar flow, the velocity distribution across the pipe is parabolic, the maximum velocity occurs at the center, and velocity decreases toward the walls due to viscous drag. The Hagen-Poiseuille law relates the volumetric flow rate to pressure drop, viscosity, and pipe dimensions for laminar flow. This is particularly useful in microfluidics, biomedical engineering, and lubrication systems. 4. Types of turbulent flow and viscous sublayer. In turbulent flow, energy is lost not only through viscous shear but also through mixing and eddy formation. Close to the pipe wall, however, there exists a very thin viscous sublayer where viscous effects dominate. This sublayer is important in determining the effectiveness of pipe coatings and roughness treatments. 5. Flow measurement in pipes. Engineers need to measure the flow rate in pipes for design, monitoring, and billing purposes. Common devices include venturimeters, use a converging diverging section to create a measurable pressure drop. Orifice plates, create a pressure drop across a thin plate with a sharp edge hole. Pitot tubes, measure fluid velocity directly by comparing stagnation and static pressures. Turbine and electromagnetic meters, for continuous and precise measurement in modern water systems. 6. Steady uniform flow in open channels. Unlike pipes, open channels have a free surface exposed to the atmosphere, such as rivers, canals, and drainage ditches. The flow is driven by gravity, and the velocity distribution depends on channel slope, roughness, and shape. The Manning equation is widely used to estimate average velocity and discharge in open channels, incorporating a roughness coefficient to represent channel material. 7. Hydraulic jumps. A hydraulic jump is a sudden change from high velocity, low depth flow, supercritical, to low velocity, high depth flow, subcritical, accompanied by turbulence and energy dissipation. Hydraulic jumps are important in dissipating excess energy downstream of spillways to prevent erosion. They also occur naturally in rivers and tidal channels. 8. Supercritical and subcritical flows. The type of open channel flow is determined by the Froude number, FR. FR 1 subcritical flow, deep and slow. FR equals 1 critical flow. FR 1 supercritical flow, shallow and fast. Understanding flow type is essential for designing weirs, gates, and energy dissipators. 9. Uniform and non-uniform flow in open channels. Uniform flow occurs when depth, velocity, and slope remain constant along the channel. Non-uniform flow occurs when any of these parameters change due to slope variations, obstacles, or control structures. We often need to compute water surface profiles to predict how depth will vary along a channel. 10. Hydraulic structures and energy dissipators. Hydraulic engineering involves designing structures to control or utilize water flow. Weirs, measure and control discharge. Spillways safely release excess water from reservoirs. Sealing basins dissipate energy from hydraulic jumps. Gates regulate flow in canals and dams. Energy dissipators are essential to protect downstream beds and banks from erosion caused by high-velocity flows. 11. Flow measurement in open channels. Common methods include weirs and flumes that measure flow rate based on water depth and structure geometry. Float methods, simple surface velocity measurement. Acoustic Doppler devices use sound waves to measure velocity at multiple depths. 12. Computation of water surface profiles. In non-uniform open channel flow, engineers use gradually varied flow equations to compute water surface profiles. These calculations are critical for floodplain mapping, spillway design, river training works. Closing summary for the course. We have now completed both Module 1 and Module 2 of this course on hydraulics. In Module 1, we build the theoretical foundation by studying fluid properties, hydrostatics and buoyancy, laws of inviscid flow, continuity, energy, and momentum equations, dimensional analysis and model theory. In Module 2, we applied those principles to real-world systems, including flow in pipes and open channels, friction and energy losses, laminar and turbulent flows, hydraulic jumps and energy dissipation, flow measurement techniques, computation of water surface profiles. By mastering both the theory and application, you are now equipped to approach hydraulic problems with confidence, whether you are designing a water supply network, calculating river discharge, or sizing a spillway.